Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Andrey Sayanskiy. Andrey received the master's degree in radio science from St. Petersburg State Polytechnic University and Ph.D. degree from ITMO University. His current research include antennas and microwave devices, computational electromagnetics, and microwave measurements. Today he will tell us about reconfigurable intelligent surfaces as effective tools for modern wireless communication systems. Andrey, the floor is yours.
Hello, once again, my name is Sayanskiy Andrey. I'm from ITMO University, St. Petersburg, and I would like to talk to you about our experience in reconfigurable in design and in study of reconfigurable intelligent surfaces. And here is outline of my talk. First of all, I start with some introduction of what it is. So what's the problem with such surfaces? What's the advantage? What disadvantage? What's the goal of using? And what is and the next is concept of one-bit reconfigurable intelligent surface, and some words regarding suppression of quantization lobes with some simulation and measurement results. So, as you know, one of the features of modern wireless communication systems is the transition to frequencies of my millimeter wave region. So it's need to increase the transmission speed and system capacity. Yes, and the second one is the development of 5G technologies lead to need massive MIMO antennas. So it means that, in other words, in comparison with systems of fourth generation, fifth and sixth generation systems, you can use antenna arrays actually to forming a set of special beams to maximize the energy transfer from base station to users. But one of the problem in work at high frequencies is high attenuation losses. Yeah, so waves attenuation at high frequencies when passing through any obstacles actually. So the issues is how to organize connection between base station and user, how to do it. So one of the concept is using so-called reconfigurable intelligent surface. It's a thin, lightweight, inexpensive device, inexpensive tools that allows enhancing the connection quality. So the base station works in conjunction with reconfigurable intelligent surface, which forming a set of beams, of many beams as you want, and each element can change his state to forming a scattering pattern of special form. So you have a good connection between base station and user, as you can see. What's the scenarios of using? Of course, RIS can work independently on base station and with connection with base station. So base station can control the RIS and to organize connection. Connection. So it's this decision can allow you to solve the problem with out of coverage, access limitation. You can divide the users with legitimate users. You can extension the coverage. You can realize multiple connection, and you can actually realize signal and power delivery for Internet of Things. Yes, and the main requirement to RIS it's cheap, it's low cost, yeah, and power efficient. So let me tell you some basics, basic facts, basic words regarding reflectarrays as a main part of RIS. To realize, to maximize energy transfer in your desired direction, of course you can use reflectarray. Yeah, and the goal is to realize, adjust the field distribution in the aperture of reflectarray to produce in particular narrow beam, or you can actually make extended beams, or maybe to synthesize field distribution to cover of a certain area. And the basic facts to realize beam in the certain direction, yeah, you can realize such phase distribution of scattering field in the aperture of reflectarray. And of course, it's phase distribution depending on the working frequency, on the period of unit cells, on requirement, reflected angle, and so on and so forth. So there are several ways to control reflection phase. Here you can see reflectarray composed from patch loads by stubs. And varying the length of the stubs, you can change the reflection coefficient phase and to realize phase distribution. Yeah. So it's a static variance without any possibilities to control the phase distribution. And varying patch size, actually. So physically, you change the resonance frequency of each cells, and the reflection coefficient phase changes. Moreover, now in RIS, using electrically tunable elements, electrically tunable reflectarray. So each unit cells of such array composed tunable element. Maybe it can be a varactor diode, pin diodes, ferroelectric capacitors. But changing the states of tunable elements, you can control the reflection coefficient phase. For example, here you can see an example of continuous phase distribution for reflectarray with certain number of elements with certain desired reflected angle. And here you can see also scattering pattern. So you can see just one beam in certain direction as you want. Yeah. Of course, in the design process, you can estimate the scattering field phase. Just calculate the reflection coefficient. So you in design process using commercial software such as CST Microwave Studio or HFSS, maybe some COMSOL multiphysics. You can consider just one unit cell with periodic boundary conditions and flocky port as a source. And here is an example of magnitude and phase of reflection coefficient for two states of elements. And you can see just varying such some parameters, you can change the resonance frequency, and you can change the phase of reflection coefficient. Challenges in RIS in terms of antennas, first of all, is realize wide work frequency band. Moreover, simplicity of the control scheme. So how to control each tunable element in each unit cell. And working at arbitrary incident angle with two independent polarization channels. Of course, the questions how to reduce losses in such device and decrease the switching time between states. So what's the element you can use? So, and moreover, the question is how to optimize the coverage for different scenarios of base station and RIS location. And of course, it's especially in at the higher frequencies, how to reduce the user location detection. Yeah, so how to minimize this time. To simplify the control scheme, to reduce the cost of the decision, so the concept of 1-bit RIS is proposed. So what means 1-bit? 1-bit means that each element, each unit cell can have just two states, all on one. Or in other words, in terms of phase, so two phases. Yeah, just two reflection phase, minus 90 degree and plus 90 degree. So the goal is to achieve the maximum values of reflection coefficient magnitude, of course, and adjust the phase shift between two states equals 180 degree in the range of control states of tunable elements. So here is the example of states distribution, in other words, phase distribution. So just a binary states. And how the phase quantization effects influence on scattering pattern, on efficient of such array. So here you can see two examples. First example is continuous phase distribution. As later, so you can see just one beam in at a certain direction. And moreover is 1-bit phase distribution and scattering pattern for such case. So here you can see, of course, main beam in certain direction, but the quantization effects leads to appear of parasitic lobe, also called quantization lobe. So in case of normal incidence of plane wave, is just a mirror lobe, and side lobes with high level. Of course, you suffer from quantization effects, but the control scheme is very, very simple. So what's about influence of phase errors? So in case of phase shift between two states is 180 degree, with increase the error different from 180 degree. So you can see appearance of mirror lobe, yeah, and reduce the efficiency in terms of directivity, of course. So to maximize the directivity, to maximize, you should to realize phase shift between two reflection states 180 degree in your working frequency band. So here's the examples of various, no more, but various examples of RIS from Greener Wave company, and here you can see Professor Matthias Fink and Dr. Geoffroy Lerousset, with his wreath composed from patches plotted by character pin diodes, and his commercial products. So products from Greener Wave company at 28 gigahertz and maybe some millimeter waves. So what's the tunable elements you can use in your wreath? So of course, the popular one is pin diodes, varactor diodes, ferroelectric capacitors, or maybe MEMS systems. Of course, using varactor diodes, you can change capacitance with changing the voltage on varactor diodes, and it gives you to adjust the states of your unit cell, and one more flexible to adjust in the final device. Another one element is pin diode. Pin diode, the disadvantage of pin diode is just two states, on or off. Yeah, and it's hard to adjust the states in the final product. After you produce your wreath, and after that you cannot to make anything to adjust states. So, but in case of pin diodes, there are low losses, actually, low losses. So here the classical examples of reconfigurable of geometry of unit cells geometries of wreath. So two examples, maybe classical patches with loaded by short circuit tabs with pin diode, and for one polarization version and two polarization version. Yeah. Of course, in the design process, you should think how to decouple the radio frequency part and DC circuit. How to, and in this case, using special decision. Disadvantages of such decisions is not applicable for two independent polarization, of course, and it's strong and characteristics of such wreath suffer from arbitrary angle of incidence plane wave. So it works just only for normal incidence, no more. For just what's certain variants of geometry. So one of the questions is how to suppress the quantization lobes. Yeah, there are two or three maybe methods to suppress. One is introduce the random phase delay in each unit cell, and in this case you can reduce the quantization lobes without affecting the directivity in the main direction. So here you can see that main pin and low value of quantization lobes. So it's high efficiency. Unfortunately, as a disadvantage is the complication of the unit cell geometry and complex design procedure, especially if you want to realize two polarization decision. Another one is method is shifting parts of the array in the direction perpendicular to its aperture. So you can, if you want, if you can divide your whole aperture on just 4 parts, no more, not 8, 16, not more, just 4 parts. You actually can, in this case, the quantization lobes split into 4 beams, and shift of 2 parts just lambda over 8. So in this idealistic case, where all the elements considered as Huygens source, so it was shown that you can decrease the value of quantization lobes without affecting the directivity. So directivity in two cases are equals. And in this case, reduction of quantization lobes by 5 dB. So what about practical case? What about practical case? So from our side, the reflect array composed of such patches, each one loaded by varactor diodes, controlled by varactor diodes, and controlled by air source. So each states of each element control. We can set the required for us states of each element through air source. So each the array composed from fully identical blocks. Each blocks composed from 4 patches. 4 patches, each one loaded by varactor diode, and states of patches controlled by information from higher distant source. So here the control scheme on the back side of the PCB plate. So you can see just for driver to control the voltage on varactor diodes, just 1 microcontroller and IR receiver. Yeah, and if each microcontroller has his own address, and if address in IR signal and microcontroller are equal, so the patches sets in desired states. So the advantage of such decision, such variant is block. So you can, it's a scalability actually. So you can realize what blocks you want without any modification of control circuits. So here is geometry of unit cell. So in this case, using using symmetrical geometry, you can in this case there are no cross polar effects, of course, and such decision there automatic decoupling between RF part and low frequency control board, and such geometry can be adjusted to work with arbitrary varactor diodes, or of course the geometry can work with pin diodes. But what about influence of arbitrary angle, arbitrary incident, oblique incident on the reflection coefficient? So in this case, here you can see the reflection coefficient, magnitude and phase for several variants, for normal incidence, for oblique incidence 30 degree, for 45 degree, and you can see that this increase the angle of incidence, the phase shift between two states is increased. So as a result, it's lost in directivity, lost in efficiency. Of course, in our case, it's as first step from our side. So there are narrow bandwidth, and strong dependence on the incidence angle. So here is our anechoic chamber in ITMO University, and we perform measurements of reflection coefficient phase and moreover scattering pattern for various scan angles, for various incident angles. So here we use horn antenna as a source of and horn antenna excite by quasi-plane wave our reflectarray, and then we measure the field distribution in the aperture of the reflectarray, and then calculation from near field to far field, we calculate the scattering pattern. Well, so here you can see results as simulated results in CST Microwave Studio and measurement, of course, and results for two cases. For case of the whole planar wreath, and for case with shifted parts. With shifted parts on lambda over 8. Two parts. So here you can see, as I said later, earlier. So you can see in this case good agreement between simulated and measurement results. You can see two beams, main beam, quantization lobe. And in this case, you see more else good agreement, and reduce the level of quantization lobes. So experimental the idea is not just to realize narrow beam in the certain direction, narrow pencil beam in narrow direction. The question is how to, in terms of phase synthesis. So it's adaptive beamforming. So, what the states of each element should be to maximize the transmission from base station to user. And in certain goals, in certain scenarios, you also can realize the field distribution of special form. For example, you would like to realize certain field distribution to maximize the coverage in certain area. So, for example, holographic synthesis, you would like to realize the certain field distribution in this area. How to do it? And for example, we can see we wanted to realize such I letter. So we see simulated results, measuring results, and good agreement. So you can synthesize, realize electric fields in the middle area of reflectarray, what you want to, of course, to extend the coverage area. And just one last results, just transmission from one antenna to another one in our anechoic chamber with one part of reflector array. So here you can see two cases of normal incidence, normal of oblique incidence, and two cases of scan angle, one, another one. So you see that in case of absence of reflector and so direct signal and with breeze. So it's in this case with certain reflector array, it's more than 20 dB. So the question also, how to estimate the user position, initial user position with minimal time. So we realize such as we call smart wall. So it's a wreath with video camera and block of video image processing. So here the example of work. So just a street with many users, and we can find the users. So we know position of each groups of users, and based on such information, you can realize the scattering pattern of such arrays to realize connection with three groups of users. So such smart walls provides real-time control with arbitrary source in radio frequency range to maximize the energy transfer. So in this case, maximum detection time with power consumption no more 5 watts. It's just 200 milliseconds. So thank you for your attention.
Thank you, Andrey, for your interesting presentation. We have a question from Alexei.
Yes, I am. Andrey, thank you so much for your talk. So I have several questions. The first one is about the phase difference. So you say for 1 bit quantization, there are two states, minus 90 and 90 degrees.
Yeah.
And the total phase difference is 180. Yeah, in fact, for example, if we consider some other frequencies, not central one, the phase difference shifts to other values, or for example, due to some imperfections when IRS is producing, for example. And do you have any estimations for the acceptable phase difference from the 180 for 1 bit quantization?
And so here, just here, now here, you can see how phase error, how of course at the central frequency you always you can realize phase shift just one reality, no without any problem. But so your working frequency range depends actually on how to phase shift decreased. Yeah. So how to error is increased. So here you can see that with error of 45 degree, so it means phase shift just 135 degree. So your efficiency reduced by 2 dB. 2 dB. 2 dB, and you have also and mirror lobe in this case also appears.
Okay. So if the phase difference decreases, so you create another mirror lobe.
Of course, yeah.
Okay.
So if you have just uniform structure, yeah, so you have just mirror loop, no more. Yeah, you cannot to operate the forms of sketching pattern.
Okay, thank you so much. So I guess we can ask questions in a round robin manner. I want to talk. I don't want to occupy the channel at all. Thank you.
Okay, the next question is then from Ilya.
Thank you so much for presentation. So my question is, so what is the effect of the inaccuracy of shifting the heights of different plates on the final antenna gain? So yes, from the slide, yes.
So you mean the difference between simulated and measured, or what?
So no, I mean inaccuracy of physically shifting. So if you wrongly shift the one plate, so what is the difference on the final gain?
If I understood you, so efficiency of quantization loop reduction is not strong dependence of such shift value.
So okay, thank you.
Okay, I guess Alexei has one more question.
Yeah, so let me continue. In your research, you consider an IRS to steer the beam in the proper direction to increase the capacity or a signal-to-noise ratio on the receiver. Did you consider other applications of IRS, for example, for some absorption purposes or sensing and so on?
No. In terms of IRS, no.
Okay. And other case, so you study here only IRS for millimeter wave or for sub 6 gigahertz? I see.
Here sub 6G gigahertz, and now we are working on RIS for 25 gigahertz, and we wait production of PCB plate from Resonance, and I expect that at the end of the August we will have experimental results with RIS at 25 gigahertz.
Okay, great. So, and is there any differences between architectures for IRS for sub 6?
Of course. In terms of tunable elements at millimeter waves, it no more not high possibilities. So just one type of varactor diodes, one type of pin diodes, no more. And the problem actually in size of such elements. So in case of sub 6G, yes, your unit cell. No, for example, in this case, period of the size of unit cell is just 15 millimeters. Yeah. With size of varactor diode no more than 0.7 millimeters. But in case of millimeter wave, the size of unit cells just 5 millimeter, and size of varactor diodes or pin diodes 0.7 millimeter.
Okay,
So the size of unit cell reduced, but they stay the same.
Okay, and if we are talking about the sizes, did you consider some mutual coupling effects if we consider, for example, one unit cell which is alone and the group of unit cells which makes a RIS? So is there some effects? Yeah.
Of course, in the design process, you consider, you simulate unit cell with periodic boundary conditions. So, of course, I understand you.
So periodic boundary conditions is enough for studying mutual coupling and modeling IRS?
For estimate.
Okay.
For estimate, yes, but the accuracy, it's a question. No problem at normal incidence, but in oblique incidence, it's some trouble, some problems.
Okay, and these troubles and problems, they depend on the difference between the periods of IRS. If we consider the size of a wave.
No, it's a problem with mutual coupling. Yeah, that and the various behavior in case of incidence in E plane or H plane, or TE or TM polarization states.
I understand.
Various behavior of reflection coefficient.
Okay. Yeah.
Due to mutual coupling.
Okay, the next question from Nikolai.
Yes. I have a question about the magnitude reduction. So these results which were presented are for like 5 gigahertz band, right?
Yeah.
And well, my question is like, what is your expectation about such magnitude reduction in case of millimeter wave transmission?
Reduction. Sorry, reduction of quantization lobe or reduction in magnitude in efficiency.
Yeah, in efficiency, like the magnitude reduction. You had some.
So losses. You mean losses at millimeter wave?
Yeah. Yes, yes. Do you expect it to be higher than in 5 gigahertz case, or like? Because like in these graphs, well, it seems that the power losses are quite high.
It depends on many factors. It depends on the tunable elements what you use. In our experience, using liquid crystals for RIS application at frequencies up to 90 gigahertz, so the loss is no more 2 dB actually for normal incidence. Of course, the losses depends on many factors. Factors of elements what you use. Yeah, so in case of varactor diodes, various firms, various companies, it depends on. So the losses depends on the characteristics of tunable elements. Yeah, and from geometry of your unit cells. Of course, if you want to miniaturize, to reduce the period and miniaturize the geometry, your resonant elements, so of course your losses will increase. Yes, but many factors, of course. But plus minus millimeter, maybe some, no more.
Oh, okay, okay, thank you. So, and but in general, like, can we expect the magnitude reduction to be like close to 1 in case of perfect implementation of RIS elements, or such power reduction will be, this coefficient will be like 0.5 or even less? Can we expect like near 1 magnitude reduction coefficient in the future?
Expect, sorry, I don't understand you, sorry. Can you repeat your question?
I mean, in the future implementations of RIS elements, which best values of magnitude reduction can we expect? Or
good question, actually. Good question. So in my experience, I can tell you that you can do the risk with losses no more 2 dB at 25 gigahertz as the whole working frequency range for any incident angle up to 45 degrees. So in my experience. But such value depends on the tunable elements which you use. So for pin diode, in our case, it's no more 2 dB. 2 dB in the whole frequency range. But for varactor diode, the losses can be much higher. Of course, you can estimate just finding the characteristics of tunable elements which you want to use. We characterize the elements experimentally.
okay, thank you.
Okay, the next question from my side. As we can see in the slide, the pictures of simulated pattern and measured pattern are rather similar, but there is still some difference. For example, we see some lobe in the center on the right picture. So what's the main reason of these differences? Is there some, because of some imperfections of the production of the reconfigurable surfaces?
No, just measurement results, just measured reasons. Because in simulation you use plane wave as a source. So here in simulated we simulate the whole array with using time domain solver in CST Microwave Studio, and the source is plane wave. In case of measurement, so due to limited size of the anechoic chamber, so the excitation phase front of our wrist is not plane wave, but just spherical wave. Yeah, and just limited size from horn antenna to reflector array explain the reason of appear of mirror lobe and the difference in directivity, simulated results and measured results.
But the developed tool, the tool you use, CST Studio, does not allow to simulate some other forms of signal, only planar.
Why not? We can do it, but in this case, it's not required. It's not so important, actually.
Okay, thank you. Any more questions? So I guess that's all for today. Thank you, Andrey, for your interesting presentation. I want to thank also all the listeners for participation. See you at the next seminar. Goodbye.
Thank you.